Hello, I'm Nicholas Mee. Welcome to the Cosmic Mystery Tour. I'm going to be talking about black holes. Black holes are amazing objects and we know that they really are out there. But there's a lot of nonsense that's talked about black holes, so I'm going to be addressing some of the widely held misconceptions about them. This is the first in a series of videos called the 4.5 biggest fallacies about black holes. In this video I'm going to be talking about the shape of black holes. Black holes are often represented as though they are sinkholes in the ground, and this is completely wrong. In the UK, our coinage includes this 50p coin, and this particular example was minted a couple of years ago to commemorate the life of Stephen Hawking. And we can see that this image shows what looks like a hole in the ground. But as Stephen Hawking was not noted for his potholing skills, we have to assume that this is supposed to represent a black hole. It is not only the Royal Mint that have fallen victim to this fallacy. This image is on the BBC's website. This one is from Sky News. And this is from the website of the US National Radio Astronomy Observatory. They really should know better. Here are another couple of examples. Attractive they might be, but even allowing for a large dose of artistic license, all these images are seriously misleading. Black holes are, in fact, spherical. This NASA JPL Caltech image is much better. It shows the spherical black hole embedded within its swirling accretion disk. What this image does not show is that the strong gravitational field of the black hole would act as a lens, very much like the glass lenses that we are familiar with. Light rays bend around the black hole as its gravitational field warps the space-time in its vicinity. This image represents this effect very well. It shows the cross-section of a black hole and how the light rays from beyond the black hole to the left are bent around the black hole towards a viewer positioned to the right of the image. This animation shows this effect as a black hole passes across a dense field of background stars. One reason for the persistence of this fallacy might be the often used demonstration of a bendy rubber sheet to illustrate the space curving effects of gravity. In such demonstrations, a heavy ball is used to warp a taut rubber sheet, rather like someone standing on a trampoline, while another mass travels over the rubber sheet around this weight. Here we have a computer generated version showing a central star warping the rubber sheet as a Jupiter-like planet orbits. Illustrations such as these are fine for communicating the general idea of how mass warps space and how this affects the paths of other nearby masses, but I'm not entirely comfortable with them. We must remember that this is simply an analogy and not a precise picture of what general relativity says. One reason for feeling slightly uncomfortable about the analogy is that it is the Earth's gravity that is pulling down the mass and distorting the rubber sheet. The warping is not due to an intrinsic property of the mass at the centre of the sheet. Another issue is that the rubber sheet is two-dimensional while the masses resting on it are three-dimensional, which might give a false impression of the way gravity curves space and perhaps perpetuate the misunderstanding of a black hole's shape. The spatial curvature, due to the gravitational field of a spherical mass, is in fact spherically symmetric. It is difficult to imagine curved three-dimensional space as we live within those three dimensions. Often physicists reduce the number of dimensions to aid visualization, so curved space is sometimes represented as a warped two-dimensional sheet. This is fine as long as we remember that the curved surface actually shows just one slice through physical three-dimensional space. The resulting surface looks similar to the rubber sheet of the earlier analogy, but now we can ensure that the slice genuinely represents the shape of a two-dimensional slice through space both outside and inside any massive bodies. It is also worth remembering that we have actually lost 2 dimensions because general relativity describes gravity as the curvature of 4-dimensional space-time. What this means is that time passes at a different rate depending on where we are in the gravitational field of a massive object. It actually slows down as we fall deeper into the gravitational well, but we won't concern ourselves with the implications of this here. This animation represents a slice through the curved space in and around an extremely dense body such as a neutron star. This slice could be through the equator of the neutron star or any other plane that passes through its centre. The blue region represents the space outside the neutron star and the bright orange region represents the space within. The steepness of the sloping surface indicates the size of the Newtonian force. In empty space outside the neutron star, the steepness increases, which in Newtonian terms corresponds to the increasing strength of gravity as we approach a massive body. When the slice enters the neutron star, the steepness decreases until at its very centre the slope is 0. This precisely matches the Newtonian picture in which the gravitational force within a massive body decreases as we move towards its centre. But don't forget that the neutron star is spherical and we have arbitrarily taken a slice through the space in and around it. The slice could have been in any direction and the way that it curves would be exactly the same. If the mass of the neutron star increases, perhaps by accumulating matter from a companion star, then it might eventually reach a point where the structural forces that support it can no longer resist total collapse under gravity. The neutron star now contracts indefinitely and is transformed into a black hole. So the neutron star, which is spherical, collapses to form a black hole, which is also spherical. The animation now shows a slice of curved space in and around the black hole. Around the black hole, the space exterior to what was the neutron star is unchanged, but now the solid surface of the neutron star is gone. There is no longer any solid body where the inexorable increase in gravity might be arrested, so the slope just keeps on increasing as we enter the abyss of the black hole. Our knowledge of what happens within a black hole is limited, but one thing we know for sure is that the event horizon of a black hole is spherical. I hope the video has shed some light on the mysteries and misconceptions of black holes. And please join us again on the Cosmic Mystery Tour, where we'll be looking at another of the biggest fallacies that are held about black holes. Thank you for watching. I'm Nicholas Mee. May the force be with you.